Hello everyone. Today we are going to discuss about the structure of benzene. The structure of benzene, the important topic of benzene. So the molecular formula of benzene is C6H6. Okay, and benzene has how many carbon atoms? 6 carbon atoms. Okay, actually, if you take alkane with 6 carbons, alkane with 6 carbons is what? The paraffin with 6 carbons is what? Hexane. Hexane formula C6H14. C6H14. But here formula is what? C6H6. How many hydrogens less than the corresponding paraffin? Corresponding paraffin means hexane to benzene with 6 carbons. Now benzene has 6 hydrogen atoms, but corresponding paraffin has what? 14 hydrogen atoms. Now how many hydrogens are lesser than the corresponding paraffin to benzene? 8 hydrogen atoms are lesser than the corresponding paraffin. Okay, benzene has C6H6, but the paraffin with the 6 carbons, hexane has C6H14. So 8 hydrogens lesser here. 8 hydrogens lesser means degree of unsaturation. DOU stands for degree of unsaturation. Degree of unsaturation is 4. For every 2 hydrogens deficient, 1 degree of unsaturation is observed. So here 8 hydrogens are deficient to benzene than corresponding paraffin. Therefore, 8 hydrogens indicating what? Degree of unsaturation 4. Degree of unsaturation 4 means the C6H6 benzene, if it is imagined to contain open chain structure, suppose if benzene is supposed to have open chain structure, suppose, okay, that should have how many double bonds here? 4 double bonds should be there. Degree of unsaturation 4 indicates what? 4 double bonds should be present in open chain with C6H6, or 2 triple bond may be present in the open chain structure to benzene. Suppose if it is supposed to be having open chain structure, it can have 4 double bonds for degree of unsaturation 4, otherwise 2 triple bonds. For every triple bond, the degree of unsaturation is 2. For every double bond, degree of unsaturation is 1. For every ring, degree of unsaturation is 1. So in this way, here 2 triple bonds may be present. 2 triple bonds means 2 plus 2, degree of unsaturation 4. 4 double bond means 4, degree of unsaturation. Or 1 triple bond and 2 double bonds may be present. 1 triple bond means degree of unsaturation 2, and 2 double bonds means again degree of unsaturation 2. 2 plus 2, 4. So in this way, any one of these possible structures of open chain type may be given to benzene. But we have observed that the properties of benzene, whatever is available in the nature, are different from the properties of open chain structures proposed to this. Okay, the open chain structure with 4 double bonds, open chain structure with 2 triple bonds, or open chain structure with 1 triple bond and 2 double bonds, they are not having similar properties to that of benzene, whatever is available. So open chain structures cannot be taken. So they are failed structures to explain what the structure of benzene. Next, another scientist here, Kekule structures. So Kekule's structure, if you observe, okay, the benzene is cyclic structure. Benzene is having cyclic structure according to Kekule. Okay, in this here, alternate double bonds are present. Alternate double bonds are present in the ring. And to every carbon atom, 1 hydrogen is attached. To every carbon, 1 hydrogen is attached. And carbon-carbon bond length, the bond length between carbon-carbon is observed to be 1.4 angstroms between any 2 carbons. Remember, between any 2 carbons. Here, he said that double bond will be the pi containing 1 pi bond. The pi bond is shifting like this. This pi bond will shift to this place. This pi bond will shift to this place. This pi bond will shift to this place. So the pi bond positions are alternatively changing here. Means what? Double bonds present at alternative position here. So the position of double bond is not fixed. The delocalization of pi electrons will be going on. So because of this resonance, what happens now? The bond length between any 2 carbons is observed to be 1.4 angstroms only. Don't take that the double bond, carbon-carbon double bond length is less, carbon-carbon single bond length is more. So between any 2 carbons in the benzene of Kekule structure, it is observed to be having 1.4 angstroms between the carbons. Carbon center to carbon center, the distance is what? 1.4 angstroms. And CH bond length. CH bond length is observed to be 1.09 angstroms. Okay, so it is Kekulé structure. And according to Kekulé structure, 6 hydrogen atoms present in benzene are equivalent. All the 6 hydrogens are equivalent. Okay, that means when we add chlorine to this, what happens now here? The chlorine replaces one hydrogen, any one hydrogen. Okay, the chlorine atom replaces any one hydrogen to form monochlorobenzene. That means mono substituted benzene. Mono means one. Mono substituted benzene means any one hydrogen atom is substituted by other group. Okay, so one group is substituted in the place of any hydrogen here. All 6 hydrogens are equivalent. Any hydrogen can be replaced by the group. That's why it is what now we can say that 6 hydrogen atoms in Kekulé structure are equivalent hydrogen. Okay, and according to this structure, it forms what now? Kekulé structure forms 3 isomers. The Kekulé structure forms 3 isomers of tri-substituted or di-substituted. Tri-substituted product, otherwise di-substituted product. If you add halogen to benzene, already one halogen is added, suppose here. One more halogen can be added. That is di-substituted. If 3 halogen atoms are substituted, that is called tri-substituted. Okay, any other group, if 3 groups are substituted in the place of 3 hydrogen atoms, that is tri-substituted product. If 2 groups are substituted in the place of 2 hydrogen atoms, that is di-substituted product. So what here, the Kekulé structure is supported by the formation of what? 3 isomers of tri-substituted products or di-substituted. Here 3 isomers of di-substituted, 3 isomers of di-substituted or tri-substituted may be formed here. So the formation of di-substituted and tri-substituted compounds indicates what now? The benzene has Kekulé type of structure. So Kekulé structure is supported by the formation of di-substituted and tri-substituted compounds. That is one thing to understand. So next thing is that the benzene can be given different resonating structures. Benzene can be given different types of resonating structures here. So benzene can be allotted different types of resonating structures such as what? Here, these two are Kekulé structures. These two are what? Kekulé structures, because the pi bond position will be changing. Here pi bond is there, the pi bond may be coming here. This pi bond will go here. This pi bond will go here. Like this, pi bonds are rotating here. So these two structures represent what? Kekulé structures. And these are called DEWAR. 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 DEWAR structures. So DEWAR structures possible and Kekulé structures possible here. So 1, 2, these 3 are what? DEWAR structures. DEWAR structures. These 2 are Kekulé structures. Okay, and also benzene can have double bond, means double bond 2 times here, 2 double bonds, and 1 carbon with negative charge, 1 carbon with positive charge. Again, this positive charge may be here, negative charge may be here. So any one of these will come under what? Resonating structures. So benzene can have different types of resonating structures. So these 2 are Kekulé structures, and 1, 2, 3. These 3 are DEWAR structures, and these are charged species. So these all come under what? Resonating structures of benzene. Otherwise, we say canonical forms. Resonating structures we can say, or canonical forms we can say. So canonical forms: 1, 2, 3, 4, 5, 6, 7 structures. Structure 1, 2, 3, 4, 5, 6, 7. So these all structures are resonating structures are canonical forms. So these all canonical forms will give rise to one resonance hybrid. One resonance hybrid of this type. This resonance hybrid of what? Benzene. That means what? This circle inside the benzene ring indicates what? Benzene circle indicates what? Benzene nucleus inside one ring indicating that the pi bonds are rotating here. The pi bonds are rotating. Means what now? The shifting of pi bonds taking place here. The shifting or delocalization of pi electrons taking place. That is why we get resonance hybrid of benzene. So these 7 will contribute what? Resonance hybrid. We will give rise to one structure called resonance hybrid, which is very close to actual structure of the benzene. So here, among all these resonating structures, otherwise canonical forms, these 2 Kekulé structures will contribute 80% to the structure of benzene. To the structure of benzene, which resonating structures will be giving more explanation. Kekulé structures. The Kekulé structures will contribute more information, more contribution towards what the structure of the benzene. Okay, so these two are major structures of the benzene we can take. And here the resonance energy of benzene is what? 36 kilocalorie per mole. That means that the resonance energy is nothing but the energy of this resonance hybrid and more stable resonating structure. The energy difference between resonance hybrid energy and the energy of more stable resonating structure. The difference of energy is called what? Resonation energy or resonating energy. So this resonance energy of benzene is 36 kilocalories per mole. Okay, so more the resonance energy, more is the stability of the molecule. So benzene is more stable due to resonance. Resonance means what now here? The delocalization of pi electrons is due to what? Conjugation of pi bond with pi bond. So one pi bond, other pi bond at alternative position. Na? This is called pi-pi conjugation. Due to pi-pi conjugation, resonance phenomena takes place here. Okay, and the resonance energy is the difference in energy between the energy of what? Resonance hybrid and more stable resonating structure. That difference is how much here? 36 kilocalorie per mole. Then HOH means heat of hydrogenation. Heat of hydrogenation means when we add hydrogen to benzene. In benzene, how many pi bonds are there? 1, 2, 3 pi bonds there. To make one pi bond disappear, two hydrogens to be added. Two hydrogen atoms are to be added to disappear, to make one pi bond disappear. Okay, 3 pi bonds should be disappeared to make it into saturated. To convert it into saturated with all single bonds, what we have to do? We have to remove these pi bonds here. To make the pi bonds disappear, 3 pi bonds disappear, how many hydrogen atoms required? 6 hydrogen atoms required here. When we add 6 hydrogen atoms to this, 6 hydrogen atoms means how many molecules? 3H2. So 3H2 when we add to this, okay, we get saturated compound, that is what? Alicyclic cyclohexane is formed. Alicyclic cyclohexane. The double bonds become what? Single bonds. So the cyclohexane is formed from benzene by adding 3 moles of hydrogen. So when we add hydrogen to this benzene, some amount of energy is released. That energy released is called what? Heat of hydrogenation. So heat of hydrogenation of benzene is how much? 49 kilocalorie per mole. 49 kilocalorie per mole means to 1 mole of benzene, when we add 3 moles of hydrogen, 3H2, we get cyclohexane. In that process, some amount of heat energy released is what? Heat of hydrogenation. Heat of hydrogenation. That is 49 kilocalorie per mole. Okay, so the heat of hydrogenation is greater, indicating what? More stable is the structure. So more the heat of hydrogenation value, more stability of the benzene. So in this way, resonance energy and heat of hydrogenation, from these values we can understand that benzene has stability. The resonance makes benzene more stable. The heat of hydrogenation value of benzene indicating that benzene is more stable. More stable means what? Less energy. More stable is indicating what? Lesser in energy. Okay, so these values you have to remember. HOH means heat of hydrogenation of benzene is 49 kilocalorie per mole, and the resonance energy of benzene is 36 kilocalorie per mole. And what is the carbon-carbon bond length? 1.4 angstroms. And what is carbon-hydrogen bond length? 1.09 angstroms. How many pi bonds in benzene? 3 pi bonds. How many double bonds? 3 double bonds. Now every double bond will contribute degree of unsaturation 1. Every double bond will contribute 1 degree of unsaturation. So 3 double bonds, 3 pi bonds. 3 pi bonds what? 3 double bonds indicate 3 degree of unsaturation. And one ring is there. The benzene is ring-like structure. One ring is equal to 1 degree of unsaturation. So for one ring, degree of unsaturation 1. For 3 pi bonds, degree of unsaturation 3. 3 plus 1, the degree of unsaturation of benzene is 4. So that point keep in mind. Next thing, the structure of benzene can also be explained by using molecular orbital theory. So molecular orbital theory can be applied to explain what benzene structure. So we can use resonance theory or valence bond theory. Valence bond theory we can use, VB theory means what? Valence bond theory or resonance theory. Any one of these two can be used to explain what? The structure of the benzene. We can also apply what? Molecular orbital theory can be applied to explain what the structure of the benzene. Structure of the benzene can be explained by using what? Molecular orbital theory. According to this, now here. Now, how many carbon? 1, 2, 3, 4, 5, 6 carbons here. 1, 2, 3, 4, 5, 6. 6 carbon atoms in benzene. Okay. Now, first you draw one single bond. C single bond C, C single bond C, C single bond C, all single bond. Okay. Carbon carbon single bond indicating which bond? Sigma bond. Carbon carbon single bond is what? On sigma bond. Imagine. Okay. And every carbon in benzene undergoes sp2 hybridization. Totally 6 carbon atoms in benzene will be 6 sp2 carbon atoms. So how many sp2 carbon atoms in benzene? Totally 6 sp2 carbon atoms present in benzene. sp2 meaning what? In each carbon atom in the outermost orbit, one s orbital intermixes with 2 p orbitals. Totally how many hybrid orbitals are formed? 3 hybrid orbitals are formed. So every carbon has what now? 1, 2, 3 hybrid. So how many sp2 hybrid? 3 sp2 hybrid orbitals. Okay. Now one s orbital mixed with 2 p orbitals only. But actually, how many p orbitals will be present in the outermost orbit of benzene of carbon? 3 will be there. 2px, 2py, 2pz. Out of 3 p orbitals, how many involved in hybridization? Only 2 involved. Still one pure p orbital is left over. So in this carbon now here, 3 sp2 hybrid orbitals are formed and one dumbbell shape will be there. One dumbbell shape is what now here? One p orbital. One pure p orbital will be present and 3 sp2 hybrid orbitals will be present in every carbon. So now what happens is that sp2 carbon of sp2 hybrid of this carbon and sp2 hybrid of this carbon, sp2 hybrid orbital of this carbon, sp2 of this carbon will overlap by axial overlapping. Axial overlapping means which bond is formed? Sigma bond is formed. So between any two carbons, one sigma bond is formed by the overlap of sp2 hybrid orbital of one carbon and sp2 hybrid orbital of the adjacent carbon. So like this, sp2 sigma bond will be formed between carbon atoms. So between any two carbons, the sigma bond is what? sp2 sigma bond. Is that clear? Now after this sp2 sigma bond formation, now see, this carbon has totally 3 sp2 hybrid orbitals like this. 1, 2, 3 hybrid orbitals. So this carbon has 3 hybrid orbitals, sp2. So one sp2 overlapped with this carbon, one sp2 overlapped with this carbon, one sp2 overlapped with this hydrogen. So sp2 hybrid orbital of this carbon and s orbital of hydrogen. S orbital of hydrogen, sp2 hybrid orbital of carbon. So sp2 s sigma bond this one. This sigma bond between carbon hydrogen is what? sp2 versus s bond, sigma bond. And this sigma bond is what? sp2 sp2 of this carbon, sp2 of this carbon, sp2 sigma bond this one. But this sigma bond is what? sp2 sigma bond. Like this, every carbon has involved in 3 bonds, 3 sigma bonds formation. Every carbon has formed 3 sigma bonds. In the 3 sigma bonds, 1 sigma bond is with hydrogen, 2 sigma bonds with 2 carbon atoms on either side. So next one is that, next, in every carbon, what is there now? One pure p orbital is left over. You see here, pure p orbital, pure p orbital, pure p orbital. So 6 pure p orbitals on 6 carbon atoms. On every carbon, there is one pure p orbital is available. Okay. Now here, this p orbital, both are parallel to each other. You see, parallel to each other. When p and p are parallel to each other, which type of overlap is possible? Sideways overlap is possible. Lateral overlap, otherwise sidewise overlap takes place. So because of sidewise overlap, what happens? One pi bond is formed. P pi bond. Which pi bond it is? PP pi bond. So here one PP pi bond is formed. Here also between these two p orbitals, PP pi bond. One pi bond is here. Okay. Here between this dumbbell shape, this p orbital and this p orbital, also what? One pi bond is formed. So like this here one pi bond is formed. Here one pi bond is formed. Here one pi bond is formed. So between these two carbons, one pi bond. Between these two carbons, one pi bond. Between these two carbons, one pi bond. So in this way, so 3 pi bonds are developed here. So 3 pi bonds are formed due to what? P and P overlap, PP overlapping. So this is orbital diagram of what? Benzene. So every carbon has 3 sp2 hybrid orbitals, 1 pure p orbital. Here 1 sp2 hybrid, this one. Here 1 sp2 hybrid. Here 1 sp2 hybrid. 3 hybrids. Then 1 pure p orbital. Okay. So in this way, what now here the alternate double bonds are formed here. Alternate double bonds are produced in benzene ring. So this way the orbital diagram of benzene can be explained here. So tell me, how many carbon atoms in benzene? 6 carbons. All the 6 carbons undergo which type of hybridization? sp2 hybridization. sp2 hybridization is nothing but intermixing of one number of s orbital with two number of p orbitals to form 3 hybrid orbitals of sp2. So like this, what now every carbon has got, every carbon atom has got 3 sp2 hybrid orbitals and one dumbbell shaped pure p orbital. Okay, now totally how many pure p orbitals in this? How many pure orbitals totally? In every carbon, one pure p orbital is there, right? In every carbon, one pure p orbital. 6 carbon atoms, 6 pure p orbitals. Next, every hydrogen has one s orbital, one s orbital. One s orbital is pure s orbital. Okay, so every hydrogen is equal to one s orbital pure. So 6 hydrogen atoms total in benzene. 6 hydrogens contain 6 pure orbitals. So 6 pure orbitals from 6 hydrogen atoms and 6 pure p orbitals from 6 carbon atoms. Totally 6 plus 6, 12 pure orbitals present in benzene. Next, how many hybrid orbitals are present in benzene? They ask you. Each carbon atom has how many sp2 hybrid orbitals? 3. Totally how many carbon atoms here? 6 carbons. 6 carbons into 3 in each. Okay, so 18 hybrid orbitals are present here. 18 hybrid orbitals are present in benzene and 12 pure orbitals are present. So they ask you sometimes the ratio of pure orbitals to hybrid orbitals or reverse. It may be asked here pure to hybrid or hybrid to pure orbitals ratio. So pure orbitals how many? 12. Hybrid how many? 18. So this is the ratio of what now here? The what here? Pure orbitals to hybrid orbitals ratio. Is that clear, ma? So it's about what now here? Okay, it is about what now here? The what here? Ratio of pure to hybrid or hybrid to pure. Anything will be asked today. So it is about what now? Hybridization of each carbon atom in benzene. So this is what now here? Molecular orbital diagram. Molecular orbital diagram of benzene molecule. So in this way we can explain what? The structure of the benzene. So generally, if you take open chain structure of benzene, why we are not assigning open chain structure to benzene? Because the properties of benzene are not similar to alkenes and alkynes. Alkenes and alkynes are what? Aliphatic unsaturated compounds. Aliphatic open chain unsaturated compounds. They have one type of unsaturated properties. And benzene is also unsaturated compound. Benzene is also unsaturated compound with 3 pi bonds. But benzene's properties are different from the properties of unsaturated alkenes and alkynes. Okay, so the open chain structure of benzene is not correct to explain it. So the properties of benzene, the structure of benzene can be explained by using what now here? Molecular orbital theory or valence bond theory or resonance theory. And who gave the correct structure of the benzene for the first time? Kekulé. Kekulé's structure is taken as what? The appropriate structure of the benzene. So benzene has different types of canonical forms like Kekulé structures and Dewar, D-E-W-A-R, Dewar structures. The Dewar structures and Kekulé structures, which will be more stable, which will contribute more to the structure of benzene. Kekulé structures contribute more towards the structure of the benzene. So this way we have to understand what? The structure of the benzene. And what is the heat of hydrogenation? I told you. Whenever 3 moles of hydrogen, 3H2, is added to 1 mole benzene, how much energy is liberated? 49 kilocalorie per mole amount of energy is liberated, and the benzene converts into what? Cyclohexane. This process is what? Hydrogenation. In that hydrogenation process, some heat is evolved. So it is called heat of hydrogenation. So heat of hydrogenation value can be used to say whether the given species is stable or not stable. At the same time, resonance energy meaning what? The energy difference between resonance hybrid and more stable resonating structure. Resonating structure is also called canonical form. So between more stable canonical form and the resonance hybrid, how much energy difference is there? That difference of energy is called what? Resonance energy, which is equal to what? 36 kilocalorie per mole for benzene. So more the resonance energy, more is the stability. So in this way, the stability of benzene can be explained. And what is carbon-carbon bond length in benzene? 1.4 angstrom. Here, due to double bond and single bond. Here, double bond length generally less, single bond length will be more. Carbon-carbon single bond length should be more. Carbon-carbon double bond length should be less generally. But here, in case of benzene, the double bond position is not fixed. The delocalization of pi electrons going on continuously. Therefore, we have to understand that due to resonance, between any two carbons, the bond length is similar. That is 1.4 angstroms is the bond length between any two carbons. Generally, carbon-carbon single bond length is 1.54 angstroms. 1.54 angstroms is what? Carbon-carbon single bond length should be there. And carbon-carbon double bond length is 1.34 angstroms. 1.34 angstroms. But here 1.34, 1.54, any value is not observed. How much is observed? 1.4 is observed. So 1.4 angstroms is in between CC, carbon-carbon double bond length, and carbon-carbon single bond length. So the bond length of benzene, carbon-carbon bond length of benzene is in between the carbon-carbon single bond length value and carbon-carbon double bond length value. So what is carbon-carbon single bond length value? I told you 1.54 angstroms. Sometimes it will be measured in picometers. 1 picometer and angstrom relation what? 1 angstrom equals to 100 picometers. 1 angstrom equals to 100 picometers. 1 angstrom is 10 power minus 10 meters. 1 picometer 10 power minus 12 meters. So 1 angstrom equals to 100 picometers. So 1.54 angstroms is equal to 154 picometers. 1.54 angstroms is equal to 154 pm, small letters, pm, picometers or picometers. Next one, here benzene has 1.40. 1.40 angstroms is the bond length between carbon-carbon, any two carbons. So 1.40 angstroms meaning what? 140 picometers. 140 picometers is the bond length of carbon-carbon in benzene. So these all things are important points to be remembered about the structure of the benzene. Once take the screenshot of this now. Just a moment. Now take the screenshot. Okay, bye. Take care.